So just to update you, today we are not going offline, unfortunately, because somebody has COVID, and I did not want to, do two things at the same time, right? So because that would be difficult to do. So we'll just give one more week. I hope by now, uh, I hope by next week, hopefully everything should be settled. If everybody else remains not sick, then we can do offline, but I cannot guarantee, obviously. Okay. So, uh, and so last class, we had a very deep look at solving the Schrodinger's equation in a finite quantum well. And also we had a look at the tunneling, how to do the tunneling probability calculations. And then I went on to talk about um, how we can have multiple barriers and physically what that means. Uh, and eventually, I said that if we have a periodic potential, that is where we start seeing many interesting effects and we become more and more realistic. Today, we're not going to do that exactly. There is one other topic that we want to cover today, and we're going to cover this today. It's called the density of states. And we're going to cover this, we're going to try to do this in 3D, 2D, 1D, and 0D. I'll tell you what this means. So we're going to cover this density of states topic. I don't know whether we'll be able to finish it in this week. Not this class. So if not, we'll finish it in next class, right? So not a problem. Uh, so what are we trying to do here? What we're trying to do here is we now imagine different kind of quantum boxes where particles are confined. Okay, so this is your 3D box, and next we can have a 2D surface. Usually the 2D surface has some thickness, but the thickness is very small. This is your 2D quantum system. And next would be a quantum wire. It's a 1D system. And finally would be a box, right? So it's a 0D system. And let me give you examples of these. So 0D systems are quantum dots. And in practice, what they can be is, let us say I have a 3,5 semiconductor of gallium arsenide. Okay, so I take an example of gallium arsenide. And inside there will be very small pockets of some other material, maybe aluminum gallium arsenide or aluminum arsenide. So these things are quantum dots. This is a quantum dot embedded in a in a gallium arsenide host, right? So this is an example. Now these are very interesting systems. Typically they use cadmium selenide, and they are now making television LED quantum dot TVs out of these. Okay, they're very bright and so on. Also, they're making photodetectors. They're making lots of devices with this. So those are the examples. And quantum, these are your nanowires. You might have heard of nanowire transistors, nanowire FETs. You might have heard of silicon nanowires. So these are very interesting from making thin transistors. There's many problems with them, but one of the things that people are really working on, 1D quantum systems. If I have 2D, I already told you, right? I sandwich a very thin layer in between two other layers. Those kind of things are actually called quantum wells. Okay, and these are actually 2D systems. Why 2D? Because here the electron is kind of free to go anywhere in the two-dimensional plane. Here the electron is free to go it's free in the one dimension, one direction. Here it is not free at all, it's bound. Here it is free to go anywhere. Okay, so based on that, the last system, this is what we see, right? It's a piece of any piece of semiconductor or a metal or whatever. This is what you can even say this, this is a classical kind of a device, right? Classical. Typically in nanoelectronics, the contacts are quite big. And so those contacts are usually considered 3D. And the channels are either a quantum well channel or it's a quantum wire channel. There are also people who are studying quantum dot channels. And these are something called single electron transistors. So imagine a transistor, right? What is a transistor? I have a source, I have a drain contact, and I have a channel in between. Now imagine this channel. In the earlier days, it used to be 3D channel, right? It's quite big. Then it became a 2D channel because the thickness got reduced a lot. Then eventually people are now studying wire-based transistors, nanowire FETs and so on. Finally, it's going to get converted into a 0D, where you might think of a small quantum dot as the channel. So this is a regime of single electrons, single electron transistors, and so on, right? Very interesting stuff. This is where the more you go, the more quantum your device starts behaving. So okay, so I hope everybody understands the idea of what is a 3D, 2D, 1D, and 0D quantum systems. Now let us come to the idea of what is this density of states. Okay, so remember, if I plot the so these are in a way you can imagine them as finite quantum wells of different dimensionality. So we know that anytime I have a potential u of x, so these are, what is the potential of this? These basically are potential u of x is 0 inside, and you can consider them to be finite outside, right? So I can write a potential function for each of these, right? How do I write a potential function for a 3D? It's going to be u x y z. It's going to be 3-dimensional. Is 0 inside, and it's going to be u outside the box, for example. Something like this, right? So these are our potentials. So same idea that we have for a one-dimensional finite well, I'm now extending it to a higher dimensions. Okay, that's all that I'm doing. And we know that how do we find out the energy trapped states? Well, we'll have to solve the Schrodinger's equation. But imagine now that you've already solved the Schrodinger's equation, right? Then what will happen after solving Schrodinger's equation? What is it that you actually get? What we actually get is we get the energy levels E1, E2, E3, and so on. We get the energy eigenvalues for that particular potential. We get the energy eigenvalues. Now we know that these energy eigenvalues, this spectrum of values, this is going to be discrete. Why is it discrete? Because we know that anytime we solve for trapped states in any kind of potential, we're going to get a discrete set of eigenstates. And so we get a discrete set of eigenvalues. There could be degeneracies. Some of these energies, there could be degeneracies, meaning more than 2 electrons could sit in each of them. These are called degeneracies. So they can be degenerate. It does not violate the Pauli exclusion principle. Okay, the reason is that first of all, we cannot have a degenerate state in one dimension. Right? That's not possible. The reason is each of these eigen states, remember, if as we did in is characterized by a quantum number n, right? So in one dimension, I can only have one. Actually, I can have two quantum numbers. One is the n quantum number, and second one is the spin quantum number. So I have each possible eigenstate in a 1D finite well can be characterized by two quantum numbers. One is a spin quantum number S, and the other one is its state quantum number. So because of this, at most um, I can have one down or one up, right? So for any given value of n, I can only have two electrons in that state. So there cannot be any degeneracies in a one-dimensional situation. But if I go to two-dimension, let's say, then I'll be specifying my eigenstate with two quantum numbers, m and n. And of course, the last number is a spin again. So you can think of, let's say I'm solving it in a two-dimensional system. Essentially, electron waves are standing waves, right? So there will be a standing wave in this direction, standing wave in this direction. Now, standing wave in each direction, I can ask how many half wavelengths are fitting inside the box. That itself is this m and n. Okay, that's all. It's not, there's nothing mysterious about it. Okay, so these are called the quantum numbers. So if I go for a three-dimensional system, then I'll have three quantum numbers, L, M, and N. And of course, the S. So I'll have four quantum numbers to specify the eigenstate of a trapped state in three dimensions. And where have you seen this? You've already seen this, right? You've already seen this in chemistry. We have these N quantum number, L quantum number, M quantum number, and the spin quantum number. They may use different notations here. Okay. And then they also have hybridization between the orbitals. So you have a sp3 hybridization, all kinds of different things happen there. We'll not go into that, but essentially any eigenstate is always characterized by four quantum numbers in a three-dimensional space. Okay. Now what can happen is that let us say state number 100 up and 210 down could have the same energy. So I don't violate Pauli exclusion because they indeed have two different. Pauli exclusion simply says that I cannot have two eigenstates that have all the same set of quantum numbers. Okay? So I'm not violating that, right? So Pauli exclusion principle does not say that does not rule out energy degeneracy. Okay, so I hope this is clear to everybody. Right. So after solving, let us say some very smart person who is very good in differential equations, let us say they have already solved this for you, right?
Can you please explain me again how Pauli exclusion is not being ruled out here?
Yeah. Do you understand the concept of quantum numbers then?
Yes.
Is this part clear to you?
Yes, sir.
Right. So Pauli exclusion simply says that no two eigenstates can have the same set of quantum numbers.
Yes, sir.
Okay. So if I go to a one-dimensional well, I have the first state, I have the second state, let's say I have the third state, right? So let us now fill it with if I fill it with electrons, this is the way I can fill it with electrons. And now I can, to each of these, I can assign a quantum number 1 up. This will be 1 down. This will be 2 up, 2 down, 3 up, and 3 down. Okay, so you got the idea of how we assign quantum numbers?
Yes, sir.
Right. So now this is one dimension, right? If I go to a, okay, let me clarify again. See, now the no two electron, if we take, there are 6 electrons possible. Take any two electrons. Either, I mean, both numbers are not same, right? Do you see that?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
So you see that all 6, what are the 6 possible numbers? 1 up, 1 down, 2 up, 2 down, 3 up, 3 down, right? Are there any any two you can pick which has the same 2 quantum numbers?
No, sir.
No, right? So in this case, it's very easy. We have not violated uh, Pauli exclusion, and we conclude that the energy states at most can have a degeneracy of 2. That means at any given level, only 2 electrons can sit, one up and one down. When we go to a two-dimensional situation, there will be there will be what are the states. Each state will now have 2 numbers. Maybe it is 1 1 up. There cannot be 0, right? We know that it cannot be 0. So one minimum has to be 1. So 1 1 up, 1 1 down, then 1 2 up, 1 2 down, 2 1 up, 2 1 down, 2 2 up, 2 2 down. Is that clear to you what I'm writing?
Yes, sir.
Right. So now, maybe see this state and this state and this state, all three could have the same energy. Right? It doesn't matter. In fact, maybe 1 2 and 2 1, it is easy to expect that they have the same energy, right? Because it's just if my shape is symmetrical, then quantum number 1 2 and 2 1 should have similar kind of energy, right? But am I violating Pauli exclusion? I'm not violating Pauli exclusion, because although the states have same energy, they are not degenerate. So I can have 3, maybe all these 4 could have the same energy, no problem. All these states could have the same eigen energy. Is this clear to you, or are you still confused?
No, sir, it's clear. I mean, I was actually confused about that only, but now it's clear. They can have same energy, but
yes, but not the same set of quantum numbers.
Quantum numbers. Yes.
Yes. Yes.
Sir, here, yes. What is the meaning of the degeneracy? That means
degeneracy matlab uska every state has an eigen value, right? Energy eigen value.
Okay, then sir, you said some like a 2 degeneracy.
That means वही बोल रहा ना. So every state has associated with it some energy, right? Eigen energy.
Yeah.
So let us say 3 of these states can have the same eigen energy. That means I can say that the energy E1 has a degeneracy of 3.
Okay.
समझ रहे हो?
Yes, sir.
It just simply means that there are multiple states with the same energy. That's all it means.
Okay. If n electron same energy, that means degeneracy is
it has a degeneracy of n degeneracy. Yes.
Yeah.
Okay?
Yes, sir. Sir,
yes.
One more thing, sir.
Yes.
Here in this last one, you say 1 1 and 1 2 and 2 1 may have the same energy level. But how can visualize this thing?
No. So I'm saying they could, right? So for that, you need to know the exact shape of the potential in 2 dimensions. You have to solve the equation, and only then you will realize that yes, that is what is happening.
Okay.
We will not know this. Okay. In fact, when we do this density of states derivation, then you will see how this degeneracy comes out. It will automatically come. Then you will realize where that is coming. So just wait for it. Okay, it's coming.
Yes, sir. Thank you.
Yes. Anything else?
No, sir.
Everybody's clear about what is degeneracy and so on, right? So, all right. So after this, whoever smart person is, they solve the Schrödinger's equation in this potential. At the end of the day, they're going to give you this particular table. They'll say energy E1 is there. What is the degeneracy of that? E2 is there. What is the degeneracy? Like this. Okay, they'll give you this table. So, and usually what happens is, see, we're going to plot this, right? So basically, you're going to plot it on the scale. You're going to use units of electron volts. Okay. And generally, the device we are interested in, we want, several electron volts we are interested in. For example, 4 electron volt range. Okay, we are interested in this energy range. And within that, there's usually a very large number of states. Okay, so we are generally not interested in what is the exact energy of a given state. That is less important. What is more important is what is the density of such states. Meaning, if I go from energy 1 electron volt to 1.1 electron volts, how many eigenenergies will I get? Okay, so why are we doing this? The reason is because generally we are interested in a very large range of, because this 4 electron volt, manlo you have a device, you are applying 0 volt to 4 volts, right? You can apply a bias of up to 4 volts, and so you need to know very wide scale of energy, and generally the between that you will have a huge number, 10 to the power 22 number of eigenenergies generally for large systems. So the specific energy of any particular solution, that's less important. What is more important is what is the density. I hope it's all clear to you. What is the meaning of density of states, density of eigenstates? Okay, is that clear to you? What is a very important concept? Okay, I hope it's clear to you now, right? And the idea comes from whatever we have done for a simple finite well. Imagine that you now extend it slightly, have more bigger system or whatever, and you solve for eigenvalues. You solve for eigenvalues of 10 to the power 23, very large number of states, and then you are not no longer interested in the individual values. You're more interested in, okay, what is the density in any particular energy region, right? So for example, 1 electron volt to 1.1 electron volt, how many possible states are there? Okay, so let us see how would we describe something like this. So what would be the units of this, right? So how we do this is the following. So and the second thing also I want to say is, generally as I increase, let's say we start with a three-dimensional object, and the bigger the object, the more the number of higher the number of possible states will be. Okay, that is why we usually want to count the states per unit volume. Per unit volume of a three-dimensional object, we want to see how many states. So how many states? This is a pure number, does not have any units. How many states per unit energy? Per unit energy per unit volume. So the units would be some number per electron volt meter cube, for example, right? Or you could have, sometimes meter cube is less used. People prefer centimeter cube in semiconductors. So it will be some number, say 10 to the power 23 per electron volt centimeter cube, for example. So let's say 1.1 into 10 to the power 23 states per electron volt centimeter cube, right? And is it just one number? No, not really, right? Because depending on like, let's say I'm plotting this energy, this is my finite well, and here I'll have different, right? So density at this energy and density at this energy will be different. So the density of states, whatever we are saying, it should be a function of energy, and it should have the units of per electron volt centimeter cube. Okay, so I hope this idea is clear to you. So if I'm considering a three-dimensional object, I'm going to consider how many energy, how the state's density will vary as a function of energy. That is also important to me. And I'm going to express it in units of per electron volt centimeter cube. Sometimes you can also put it in terms of per joule centimeter cube also. Remember, electron volts and joule, they are slightly different units of energy, but they have the same dimensionality. Okay. Okay, I hope this is clear to you. If I, this is for a three-dimensional object. If I was looking at a two-dimensional object, then two-dimensional object like this, then each little portion, right, this will have its own states, right? And so I need to be, this density I need to be doing at per electron volt centimeter squared. Areal density, right? And if I was doing it for a single wire, I would express the density as electron volt per centimeter. Per centimeter. So per unit length, one portion of this, how many allowed energy states are there? That is the question. That is what this number expresses. At any given energy, in this little portion, in a very small band of energies around that particular energy. For example, if I tell you at 1 electron volt, maybe you will consider, okay, 1.99 electron volt to 1.01 electron volt, for example. How many bands are there? How many allowed states are there? And that window, you go 10 to 0 basically, right? So it is basically limit of epsilon tends to 0. How many states are there between E plus epsilon and E minus epsilon? So that is why it has to be a function of this E, right? It should not be a function of epsilon because we take the limit tends to 0. Okay, so that is the idea of what is density of states. Why is this important? This is important because if you know the density of states and if you know the probability of those states being occupied, you multiply the two, that will give me the total number of carriers found at that particular energy. That's it, right? And you integrate that, this is how you get the carrier concentration. So remember, we have this Ni squared, N into P, Ni squared, everything, everybody would have done this, right? This is exactly how that's done. You start with the density of states, then from density of states, you multiply that by the Fermi-Dirac probability. So this is like calculating how many empty seats are there in a big auditorium. Then depending on the temperature, people will, a seat will be either occupied or not occupied. So you multiply the two, then you get the total occupancy, right? Any doubts about what the meaning of density of states is? Yeah, I hope it's clear, right? It's fairly clear.
What about the 0D?
In 0D, what happens is, yes, good question. So in 0D, what happens is that there is, first of all, there is no volume for 0D, right? Because it's a point, right? Ideally. So we cannot define this function, density of states, for that. And what will happen there is you'll have a discrete set of energies. So the density of states is going to be a delta function for a 0D system. Is that clear?
Yes, sir.
Okay, thank you. So let us now go ahead and do these calculations. We don't do this for realistic systems, okay? And I'll tell you later on how we can do this. For example, if you ask me, if I gave you a silicon and I made a 2D system out of it, can I exactly calculate how many density of states is there? The answer is yes, you can, but not yet. We're going to make a slight idealization. We're going to ignore the nuclei that is present in the slab. Okay, we're going to consider an ideal two-dimensional or three-dimensional potential well. We simply extend whatever we have done in 1D case. This is extending that to a 2D case. But here we are not interested in solving for the eigenstates. Not interested in that. We are more interested in counting how many eigenvalues are there. Okay. So I hope you can draw the connection between what we have done before and what we are doing in this class. So let us start first with the case of a 3D. Start with a 3D case. Okay. And so in general procedure, let me explain this. So the minus h square by 2m Schrodinger's equation, right? So that will become in general, it will start looking something like this: d square dz square into phi. Our wave function also will now have 3 dimensions: x, y, and z. Again, all this is time independent, but higher dimension, right? Plus u, which is also a function of x, y, and z, into phi, which is a function of x, y, and z, okay, is equal to e times phi x, y, z. Okay. So how do we solve this? This is very difficult to solve, right? Again, we rely on a trick. In order to solve these kind of systems, what we again use the principle of separation of variables. And so we say that this can be expressed as capital X, which is a function of X only, capital Y, which is a function of Y only, and capital Z, which is a function of Z only. Okay. And when we do this, the second and the third term are kind of easy to write, right? So let us just see what will happen to this first term. So if I do this, minus h squared by 2m d squared dx squared, if I do that to x of x, y of y, z of z, what will happen, right? So this is going to give me minus h bar squared by 2m. Y of y and z of z will just come out, and I'll have partial of x of capital X, like this. Okay, so similarly, the other terms will also, so these three sums now I can write it this way: minus h squared by 2m, x of x, z of z, d square by dy square of y of y. That's the second term here. Similarly, the last term is minus h squared by 2m, x of x, y of y, partial z of z, like that. Okay, so that is this. Next, we'll do the second term, plus u of, and here we're going to make an assumption that the u, this u is also separable. If it is not separable, then we are out of luck. Okay, so this also has to be separable. So I'm going to call it ux of x, uy of y, uz of z. So u is also separable. Otherwise, we're out of luck, right? So, and then we're going to x of x, y of y, z of z is equal to e into x of x, y of y, z of z. Looks very complicated, right? But what will happen if you now just simply divide? I just want to divide this, divide every term by this. So I've cut it up this way, right? And I cut it up this way, and then what you will get is the following. Here, if I divide by x, y, z, right? So this will cancel with this, and I'll get these terms of the form minus h squared by 2m, d square by dx squared, x of x, divided by x of x. Something like this, right? I'll get three terms, other two terms similar to that. Minus s squared d squared dy square of y divided by y, right? Or you can write it in this way also. You can write it as 1 by 1 by x into minus h square by 2m d square by dx, something like this. Okay, and remember, we are interested to solve the problem inside the box, right? So so we know inside the box the potential is 0, right? So we can even cut this out completely, and we can write it finally in the following way: 1 by x into d square by dx squared of x plus 1. I'll take the constant out later, okay? You'll get it. See, this is all capital Y, d square by dy squared into y plus 1 by z into d square by dz square of z minus h square by 2m is brought to the other side. So I can write that as minus 2m e by h bar squared. The right hand side is now a constant. Okay, so what is happening? I'm adding x. This is a function only of y. This is a function only of z. But when I'm adding these three numbers, regardless of what the value of x, y, z is, I'm always getting a constant. That is only possible if each of these is always equal to a constant. Because see, no matter what value of x, y, z you get, this equation has to be satisfied, right? That is only possible if for every value of x, this thing has the same value. Same thing for this also, same thing for this also. So I'm going to write this, finally, my Schrodinger's equation in a three-dimensional potential box inside the box where the u is 0. Inside that box, I can write it as 1 by x into t square by dx squared of x is equal to some constant. I'm going to call that as ex into 2m by h bar squared of x. Okay, and you'll immediately, and similar equations for y and z. So you'll immediately recognize this because we have already solved this. This is nothing but Schrodinger's equation in vacuum. And so I can write my complete solution now as following. Should be equal to a into e to the power minus j kx x plus b e to the power plus j ky sorry kx x. Only difference is plus and minus. This multiplied by c into e to the power plus not plus minus, the same order, minus j kyy plus d e to the power plus j kyy into, okay, this is not a cross, this is not x, okay, this is, yeah, maybe I'll just not even do this, I'll just put a bracket in, you'll realize that they're products, right? So then e into e to the power minus j kz z plus f into e plus j kz z, where a, b, c, d, e, f are constants, are just numerical constants. They have to be found by solving the differential equations, solving the boundary conditions. What are the boundary conditions? If my box is a cube like that, and it is it's a cube like that, then you know that, like wave function has to go to 0 on this wall and this wall, right? Things like that. those kind of boundary conditions you put it and you get the final answer. I have something more to tell you about boundary conditions in just a moment. There is a little bit of subtlety here, but I'll tell you more about it later on. But generally understand that A, B, C are just numerical constants which have to be found by solving for the boundary conditions. Just like what we have done before. What has happened? I'm simply getting now product of 3 solutions because they're independent in X, Y, Z. Now that's all I'm getting. Nothing confusing. But there is a caveat here, right? What is Kx? What is K sub x? K sub x is root of 2m ex divided by h bar square. Similarly, ky is root of 2m ey divided by h bar square. Kz is root of 2m ez divided by h bar square. What are these ex, ey, ez? Those are these constants that are introduced, right? And if I add all of them, I need to have a units should be preserved, right? So for example, what I said is this entire term is minus 2m ex by h bar square. This is what that's a constant that I assigned to it. So because my dimensionality has to match, what I find is E should be equal to Ex plus Ey plus Ez. So the total energy, clearly you can realize now that Ex, Ey, Ez must stand for the kinetic energies in the X direction, kinetic energy in the Y direction, kinetic energy in the Z direction respectively. Okay. Why not potential energy? Because we are solving for a potential box where inside the box, right? Where we know it's inside the box is 0. No, that's so it cannot have any potential energy. Okay. So this is clear to you. So I now express my final wave function in 3 dimensions in terms of its energy values in the X, Y, and Z directions separately. Okay. Or in terms of Kx, Ky, Kz, what is my total energy? My total energy is actually 2 h bar square by 2m into kx squared, ky squared plus kz squared, kz squared. Okay, so I hope everybody gets this, right? So it is exactly like what we have done before, except now my k, right? This actually is a vector now. It is a vector because it has a kx, ky, and kz z hat. That's all there is to it. And so my what this momentum, what is my total momentum? It's h bar k. Momentum is a vector. It has all 3 components, right? Nothing surprising there. Momentum is a vector. Okay. Yeah. Okay. I hope this is clear to you. Now what will happen is we will impose the boundary conditions, and that boundary condition will tell me exactly what value ky, kz can take. Remember, in an infinite well also we did the same thing. We realized that kx can be n pi by a, right? So similar thing like that should happen here also. That is exactly what we're going to find out. Okay. So far so good, right? What I've done is I've simply extended whatever we have done so far in the one-dimensional infinite well case. I just extended it to a 3-dimensional case. Okay. Any questions about this? Can you all hear me? Is the connection okay?
Yes, sir.
Okay, so that's not a problem. All right, so I guess it's clear. So everybody can hear this, right? Okay, fine. So So let us go on. Okay, so now I'm going to tell you a little bit about the boundary conditions. There are two kind of boundary conditions that we can use. The first that we are already familiar with, these are called the hard boundary conditions. So this basically says if I have my box, outside potential is identically equal to 0. Sorry, outside potential is identically equal to infinity. Now there is another kind of potential which are called the one Neumann boundary conditions. One Neumann boundary. One Neumann boundary, what it says is, instead of saying that the wave function actually goes to 0 outside, it actually says that it imposes something called a periodic boundary condition. Periodic condition. And I'll tell you the reason for why they do this. But let me tell you what is a periodic boundary condition, first of all. So imagine a function, imagine a periodic function, right? So periodic. So any function that is periodic, it obeys the following property. F of x is equal to f of x plus L, where L is the periodicity. Where L is the periodicity. Okay. So similarly, what we suggest, what we say here is that let us, instead of choosing a hard boundary condition for this problem, let us choose a periodic boundary condition. Okay. And why we do that? The reason is that if we choose a hard boundary condition, then my solutions are actually standing waves. That means they cannot actually carry energy from one physical location to the other physical location. And it is to avoid this that people use the periodic boundary conditions. Okay, so that is all I want to actually tell you about that. So what we're going to do now is we're going to impose periodic boundary conditions on this particular wave function. So we imagine a box. We imagine the box, size of the box is L. I'm going to make same in all three dimensions. Size of the box is L in X, L in Y, L in Y. So box of volume L cubed. Okay. And yeah, so this is how I'm going to make this. So if I impose this boundary condition, I'm going to impose that boundary condition on this particular system, right? And when that happens, let me just tell you what is going to happen, right? So if I say e to the power minus j kx x, if this function has to be periodic, then it has to follow this, it has to satisfy this equation, right? So that means e to the power minus j kx of x plus L must be equal to e to the power minus j kx of x. The only way in which I can make this function periodic, this wave function periodic, is if I ask it to satisfy this particular condition. Okay, now let us go ahead and see what this condition entails. So this condition will simply entail that e to the, this, I can break this down, e to the power kx into x minus j kx into L is equal to e to the power minus j kx into x. So this condition entails that e to the power minus j kxl is equal to 1. How is this possible? It's only possible if kx into L must be n times 2 pi. Can be plus n or minus n. Can be 0 also. Okay, that is the beauty of this particular choice. Okay. If I take kx is 0, if I take n equal to 0, then the wave, because the wave function is actually, here the wave function is no longer confined, right? It is not, it's periodic. So it actually exists everywhere in the box. And imagine the box we are putting periodic boundary condition, right? So even if kx is 0, integration of this wave function will not give me a 0 probability. So for this particular boundary condition, periodic boundary condition, values of n allowed are 0 is allowed, okay, plus or minus 1, plus or minus 2, plus or minus 3. The condition 0, what it simply means is that remember my momentum is h bar k, right? So, and p is equal to h by lambda, right? Or lambda is equal to h by p. When k is 0, that means k is 2 pi by lambda, lambda is infinite. And if lambda is infinite, my momentum is 0. So it is just talking about a wave function with a very, very low momentum. That's all. So n is 0 is allowed, and you can actually substitute here. If I substitute kx is equal to 0, then I get a plus b, and integrating that will not lead to a 0. Okay, instead my wave function was sine of kx into x, then kx is 0 would have led to a catastrophe. That is the reason why n equal to 0 is allowed for a periodic von Neumann boundary condition. Okay, little bit of a mathematical jugglery. All right, so this tells me that the kx, what are the values that kx can take? It can only take values 2n pi by L, or it can take values n times 2 pi by L. Let us say that, let us choose this number, we call it nx into 2 pi by L. Now nx becomes our x1 quantum number, becomes my x quantum number. Similarly, I can say that ky will be ny into 2 pi by L. Ny becomes my second quantum number. Similarly, I can say that kz has to satisfy nz 2 pi by L. In general, if Lx, Ly different, you can put Lx, Ly here also. Okay, but in my for simplicity, I'm taking Lx equal to Ly equal to Lz. And nz also can satisfy 0, plus or minus 1, plus or minus 2, and so on. Right, so how do I characterize any particular eigenstate? I characterize it by specifying these quantum numbers, nx, ny, nz, and s. I need a total of 4 quantum numbers. An example, can ny be 0? Yeah, it can be 0, no problem, right? So I can have quantum number like this, 0, 0, 0 up. Or I can have another quantum state 0, 0, 1, 0, 0, 0 down. Or I can have 1, 0, 0 up, 1, 1, 0 down. All these kinds of possibilities are there. We will not exactly go into try to solve for this, okay, because there's just too many such states. Remember, our purpose is to find the density of states. But I hope you understand where the states are, right? So let us now, okay, I just wanted to, another thing I want to say is, whereas if I look at possible values of kx, the first possible value is 0, next possible value is 2 pi by L, third possible value is 4 pi by L, then 6 pi by L, another possible value is minus 2 pi by L, minus 4 pi by L, and so on. These are the possibilities. Okay, so now we're going to go into a space called the K space. I'm going to go into a space called the K space. What is the K space? It is a space where it is also a three-dimensional space. It is a space where the x coordinate tells me what is the kx of my state. The y coordinate tells me what is the ky of my state. And z axis tells me what is the kx. So if I have a state, if this particular state, right? So then how do I represent that state in the K space? That's the momentum. It will be actually represented by the origin. Again, there are two here. Okay, so there is one upspin, one downspin. So there's like this. So this is called a k-space representation of any quantum, of any eigenstate for a three-dimensional box, right? So like that, let us see where do we represent the other states. Remember, I told you kx can go, difference between one state and the next state is 2 pi by L, right? So there will be a state here. Next, there will be a state here. 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 So what is the quantum number of this particular state? It is actually 0, 1, 0. Can be up or down. Okay, so are you following what I'm doing here? So then I can have states here also, right? And I can have states here also, like this. So I'm going to draw some wire here. So imagine states like that, right? So each of these states is an allowed state. So we are simply now mapping out the K for all the allowed states. These are all the allowed states. Not only that, right? Here also, this is also an allowed state. This is also an allowed state. And here this is an allowed state. This is an allowed state, allowed state, allowed state. Like this, right? So you can imagine these are allowed states. Okay, so do you imagine this? Do you imagine how the allowed states are represented on the K-space? Okay, now in the K-space, any doubts about the K-space? What we're doing in K-space? It's all clear, right? At every dot here, those are the only allowed values of K. Okay, Kx, yes.
If we choose at any axis like a x, y, a z, then all are same state. Which is like a y-axis. Then this all dot are at same state.
No, they are not the same states. No, their values are different, right? For this particular, the kx, kz values will be different. No?
But notation like a 0, 1, 0.
No, notation different, right? Na? This notation is 0, 1, 0. What is this particular quantum number of this guy? That is 1, 0, 0.
I am talking about only at same axis, like only y-axis at ky.
So this guy will be 0, 2, 0.
Okay. Yes.
Of course, no, this guy will be 0. Array coordinate axis pe distance
yes.
You got it now?
Yes, sir.
Okay. And this is the quantum number only. What is the exact value? Exact value you have to multiply by 2 pi by L. Are you getting it now?
Yes, sir.
Hello?
Yes,
you
sir.
Got it?
Yes, sir.
Okay. So, so even here, my Pauli exclusion is not violated, right? Because each dot here will have a unique set of nx, ny, nz quantum numbers, but each can have upspin, downspin, upspin, downspin. So everywhere we have upspin, downspin like this. Okay, so this is how we represent all possible solutions to the Schrodinger's equation in a three-dimensional potential box with periodic boundary conditions. And there 0 also is allowed. Okay. Right. So if I ask you, okay, for this particular state, what is the energy? How will you do it? You'll have to do h square by 2m. Find out what is the kx square. For this case, kx seems to be 0, 0 squared. Ky also seems to be 0. What is kz? Kz seems to be 0, 1, 2. So it is 4 pi by L square. That is the energy of this particular state. There will be one upspin, one downspin again. Okay, so I hope you understand now what we are doing here and how we represent the solutions of the Schrodinger's equation in the K space diagram. This space is in K. It is called the K space diagram. It's not the real space. Okay, this is the K space. Okay. How do these things look in real space? Well, that is easy to answer. This is how they look in real space, right? A into e to the power minus j kx into x. This is how they look in real space. You have to literally substitute values of x, y, and z. Take a value of kx, kz. For any given value of kx, ky, kz, take all values of x, y, and z and substitute in this. That's what going to give you a real space representation of that particular eigen state. Okay, and the K space representation of the eigenstates is here. These are all the different possible eigenstates in K space. Okay, clear? And I also told you how to calculate the energy of any particular state. Okay, now comes our question. What we want to do? We want to now count this. Okay. What exactly do we want to count? We want to count the following thing. We want to count how many states are there where with the mod, k, with the k mod of the k vector, that is distance from the origin to this particular, the mod of the k vector, for example, is the distance from here to here, right? That is the mod of this guy. How many such states are there with mod between k and plus k plus delta, some two numbers, right? How do we find that out? Well, that is easy to do. I'll have to first draw some kind of a circle, a sphere, right? Because the argument makes a little bit more sense in 2 dimensions. So I'll just show you the idea here. So imagine in 2 dimension, these are all the allowed states, right? So these are all the allowed states. Now we want to count. What I want to count? I actually want to count all the states that have energy between E and E plus DE. This is what I want to count. Okay. If it has a energy E, then it's going to have, what is going to be the mod K for that? It's going to be 2me by h bar square, right? And this, if it has energy, this energy, then its mod K will be 2me plus dE by h bar square. So how do I choose all the states which have whose mod of the K is between this number and this number? That is actually, I'm going to draw a circle like this, so that this distance is the first number. Okay. This number, I'll call it K1. I'll call this K2. So this radius is K1. And then the second number, K2, like this. This is the, okay, this is K2. So I'm going to choose only those states that fall between these two numbers. Okay. All so which are those things? For example, if I zoom in, see this particular guy is qualifying, he is qualifying. Everything that has come in between, these states have energy between E and E plus DE. Okay, that is what I want to find out. So if I take this argument now to the 3 dimensions, I can now write it in this way. Oops. I can now write it this way. Let me count the states G of K, D of K. Okay, which are states that have the mod of K is a certain number K and K plus dk, right? So this is simply given by the area of the shell 4 pi into K square and the see, this is K, right? And this radius is K plus dk. What is the area of the shaded ring? That is going to be 2 pi r into dk, right? That is in 2 dimension. In 3 dimension, what will happen? I want the volume between two spheres. Radius of the first inner sphere is K. Radius of the outer sphere is K plus dk. So that is nothing but 4 pi K squared into dk is the area of the shell between the two spheres. Okay, so this is the volume in K space. Now, if you look at each of these dots, the distance from this dot to this dot is 2 pi by L. Distance from this distance is 2 pi by L. This distance is 2 pi by L. This distance is 2 pi by L. From here to the bottom one is 2 pi by L. Here is 2 pi by L. That means I can conclude that the volume occupied by one red point here is 2 pi by L cubed. Volume occupied by one red dot in K space. That means per unit volume in K space, how many dots will I find? I'll find L cubed by 2 pi cubed dots. This is the density of allowed states in K space. But I'm interested in how many such points are lying in this particular shell. So I'm going to multiply this. So GK, the number of states that I'm interested in counting is nothing but L cubed by 2 pi whole cubed. I have to multiply this by 2 because I know that each state has 2 spin states. Okay. So what is the answer? G of K, D of K is 8 pi K squared dk into L cubed divided by 8 pi cubed. Simplifying that gives me K squared by pi squared into dk into L cubed. But remember, we are again counting per unit volume. So this L cubed, I'll remove that, right? Because I don't know. So I know that G of K, D of K, the number of allowed states is K squared by pi squared into dk. But I'm not interested in G of K, D of K. What I'm interested in is G of E, D of E. So that can be obtained by doing this number. You simply multiply by dE by dk. You multiply by dE by dk, this is going to get sorted out. Okay, and let us do that. So remember, E is nothing but h bar square K squared by 2m. So D of E divided by D of K is equal to h bar squared by 2m 2k dk, and k square by pi squared, this part is nothing but 2me by h bar square pi square. So G of E finally is given as 2me by squared into h bar squared by 2m into 2k. K is again root of 2me by h bar squared. Okay, and I'm going. This is the final answer for GE, and you can simplify this. Simplify this. you can see that it is proportional to e to the power 3 by 2. Okay. Yeah, the exact derivation. Let me show you the exact derivation. 3D density of states. So that's what, so you can see that in one dimension, now we have done 3 dimension first. So yeah, so this is the derivation that we have done. Final answer comes to I made some mistake. Yeah, sorry, I have to do dk by de, not this. Right. So I'm interested in finding g as a function of e. So g as a function of e is g as a function of k into by dk into dk by de. Right. So I have to do the reverse of this. Not that's where I made a mistake. G of k dk. This is nothing but k square by pi square. dk by de is a reverse of this. So that's 2m divided by 2m divided by h bar square into 2k. Okay. Which is proportional to k, and k is proportional to root 2me by h bar square, right? So you see that g of e, the coefficients are, I'm going to leave it to you to work it out, but it's going to come to be proportional to root of e, right? So the exact value is root 2. So g of e, exact expression, root of 2 m to the power 3 by 2 by pi square h bar square into e to the power 1/2. Okay. And what are the units? States per electron volt centimeter cube, right? Per unit energy, per unit energy, per unit volume, right? So that's what it is. These are the units. The more than the constant here, what is important is this particular expression, right? And you might have already seen it. Let us see how that goes. But we'll plot it in a slightly different way. We're going to plot the energy in the y-axis. This is my zero energy. And we're going to plot the density in the x-axis. And our energy goes up this way. So at zero value, clearly the density of states will be 0 here. And if I draw this curve, right? So this is basically my straight line, right? So it is this is proportional to E. So you'll find out that this particular distribution is going to be less than E, straight line, right? Because it's root of something. So it's going to go something like that. So in other words, it doesn't increase so rapidly. After some time, it almost kind of saturates. Okay. So it looks like a high parabola, right? The density of states looks like a parabola in a way. Uh, Something like that. Okay. So this is a square root of E dependence. Now, if I do, you have already seen a part of this. I'll show you where. Imagine this is your conduction band edge, right? And so this will tell you what is the density of states function for the conduction band in the semiconductor. So this is your G of E function. Now, the Fermi-Dirac function, let's say this is your Fermi level, then Fermi-Dirac function is going to do something like that, right? Occupation probability. When I multiply these two, I get a function that looks something like that. This is my occupation. And when you integrate this, it's going to give you Ni. Okay. So I hope you have already done this, I'm sure, just a recollection. So I hope this jogs your memory as to what is happening. This is how we do quantum density of states in a 3-dimensional. Now, once you solve it in 3-dimension, the other things are actually quite easy. Okay. The other things are becoming easy because now you can go to 2-dimension. What happens in 2-dimension? In 2-dimension, we have the wave function looking exactly like this, except there is no Z dependence. This part goes away. This part goes away. Right. And when that goes away, let us look at the interpretation. Now let's look at the K-space depiction for a 2-dimensional quantum system. Then a 2-dimensional quantum system can only have X and Y, right? It can only have Kx and Ky. It does not have Kz. And where are the allowed states? Allowed states are here, 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 like this. Again, the distance between this and this, distance between this and this is once again 2 pi by L. So in a 2-dimensional situation, what will happen? Let us see. The area occupied by one particular point is 2 pi by L squared. Okay. And thus the density for every, this is again K-space, for a unit area in K-space, how many points will you find? You will find L squared by 4 pi squared points. This is your density per K-space, basically. This is your density in K-space. Density of points in K-space. Allowed points in K-space. Now we are again seeking points between K and K plus dk, all that, right? So here in this 2-dimensional become this is your first circle and a second circle. We want to choose points that are basically in this volume. Not volume, in this annular region. What is the area of this region? That area of that region is 2 pi k times dk. And already I wrote the density, so I'm going to multiply by L square by 4 pi squared. This is the number of allowed points within this annulus. So this is my G of k multiplied by D of k is given by this. Right? You can even say G2D. KdK is given by this. And let us simplify that. So that is going to come to, I want to do per unit area. So that is where my factor of L squared cancels out. is a total number. I want a per unit area, so I per unit area divided by L square, right? That's the area, total area. Okay, this comes out to be K times dk divided by 2 pi, K by 2 pi into dk. Now I want to find G of E. So that is basically whatever this function is, dg by dk into dk by de, chain rule of multiplication, right? Chain rule of multiplication. And so what is dk by de? dg by dk is this. No, just this part, k by 2 pi. dk by de is how much? We have already done it, but let me do it again. E is equal to h square k square by 2m. dE is equal to h bar squared by 2m into 2k dk. So dk by de is 2m by h bar squared 2k, which is m by h bar squared k, which is m by h bar squared into k is nothing but 2m e by h bar squared, which is h bar, yeah, so I get, let's do it slowly. So this 1 by root of h bar squared into m into 2 into 1 by root e. Okay, so that I can write finally this entire thing as k is again root of 2m e by h bar squared into 1 by 2 pi into 1 by root of 2m h bar squared into 1 by root of e.
Sir, I think root m is in numerator.
Yeah, root m numerator में आएगा, correct. Yes, root m. 2 is still here, right? So you see e and e cancels out, and so I get root 2 also cancels out. Root 2 also cancels out. H bar square, so this will become by h bar square, and m to the power just m by h bar square, m by 2 h bar square pi. Yeah, that's it, right? So I'm getting G of E has no dependence on energy at all. So it is basically it is completely constant, basically, right? So it's a m by 2. So this is a constant. Okay, so we can see that in 2 dimension, the density of states is actually constant. Now you might have seen something different, right? We have seen a step function like this. So I'm going to explain why that step function comes about in the next class. Okay, because already, oh, actually we're not supposed to go till 6:40. So let me continue. When we were doing this 2-dimensional calculation, I skipped a little bit. Okay, so what did I skip? So if we imagine a 2-dimensional quantum system, let us examine this a little bit more detail now. We examine a 2-dimensional quantum system like this. It has a length L here, it has a length L here. But remember, I told you we cannot consider that the length along the Z is completely 0. That is simply not possible. So actually, in reality, we have to consider this as another length A, small length A. Okay. And we know that in this Z direction, the electron is completely confined. It cannot really go out at all. However, it is free to travel in this plane anywhere. So it turns out that the best way to describe this particular situation is if I define my wave function in the following way. So in x and y, I'll simply have it minus j kx into x plus b e to the power plus j kx and kx into x multiplied by c e to the power minus j ky into y plus d e to the power plus j ky into y. In the z direction, however, I'm going to say it is sine of kz times z. Okay, so I'm going to choose a standing wave in the z direction. I'm going to choose propagating. I'm going to choose periodic boundary condition in the x and y directions because the electron is in a way free to propagate there. However, I'm going to choose a hard boundary in the z direction. And we have already solved what happens in a hard boundary, right? This is our infinite potential hard boundary. It's going to be of the form sine kx, sine kzz by sine kz into z. Now, what are the conditions? Conditions are the following. Now, kx can take any value 2 pi by L into n of x, where n of x can be 0, plus or minus 1, plus or minus 2, and so on, where nx is our quantum number, a kx quantum number, and we can choose a similar thing for my y, where ny is again such and such a quantum number. That's because it is propagating in the xy. Now for the z, I'm going to do this. It's n pi by a, because this is how we did it for the remember in a finite potential well, right? Now I can say not n, actually I should do nz. Let me do this correctly. What I'm going to, how I'm going to fix this k z is nz pi by a, where a is the dimension in the z axis. Now I'm going to say that nz can only occupy value 1, 2, 3, 4. Cannot occupy negative values. Why is this happening? This is happening because on the wave function, I am imposing periodic boundary conditions on the x and y. Why? Because I want propagating states in the x and y. I don't want standing waves. I want power current to actually flow, right? But in the z, I know for a fact that electron is not escaping. So I put hard boundary on that. So, and hard boundary, we know that that quantum number cannot be occupying 0, right? It cannot occupy 0. So nz cannot be 0. But nx and ny can be 0. I hope this is clear, becoming clear to you, right? So now how do we modify our picture of the k-space representation? K-space representation picture is modified this way. In the xy plane, the points are going to be still like this, right? I'll use my red axis. So I'm still going to have points like this. Distance between them is 2 pi by L. This distance also 2 pi by L. Very clear already. However, all these states, these have nz is equal to 1 basically. Okay. What about nz is equal to 2? Where are those states? Those states are actually slightly away up here. So a similar plane like this is there up here. Okay, are you visualizing it? I hope you're visualizing it, right? So it is up here this way. They're negative also possible, okay? Negative also possible. Now the distance between this particular sheet and this particular sheet, now this is actually, you see what is the distance? pi by A. Now remember, my L is much larger than A. So 2 pi by L is much smaller than pi by A. So initially in the 3-dimension case, what was happening? I had a very nice grid like this. I had very nice grid. When I go to a 2-dimension with a very thin, with extreme quantization in the z-axis, then imagine those sheets getting separated very widely. Okay. So now we know how to count the states in this particular sheet that is given by this expression, right? I know how to count the electrons in this sheet. I also know how to count it in this sheet. Those are also going to do the same thing, right? So now we have to combine this information somehow and find the total density of states function for my entire 2D system. This is what we're going to do in the next class. Okay, so I'm going to stop here. Any questions? Okay, please have a look at these derivations and okay, just work it out. So that is all from my